So they donate their lone pair to H plus from water, and you get this NH3 plus and OH minus. So they increase the concentration of OH minus in water. So we should consider them as bases. I hope this is clear. Got it? They are bases. And to measure that, to measure their strength, that how strongly they can donate their lone pair, this is an equilibrium reaction. You know, I have put a double-headed arrow. You can see that this can be measured by its equilibrium constant Kb, right? So by Kb you can measure the equilibrium constant, and this is Kb, okay, for because we are measuring, or you can just put a simple K also, right? Or that doesn't matter. It is a measure of basic strength. So I have written the equilibrium constant. H2 is basically the concentration is constant, it is fixed. So you multiply it with it and just call it. So no need to write the concentration of H2 because that is not changing. We know that from class 11 that for pure solids and pure liquids you keep the concentration 1, okay, because they remain same. So this is the equilibrium constant Kb, and stronger base, if the basic strength increases, if basic strength is higher, okay, Kb is going to be large. Means more basic means you have more OH minus ion concentration. The amine is going to take more H plus. You have more hydroxide ion concentration, and the equilibrium will be towards the right hand side. Okay, that is basic. Next is suppose if it is more basic, more hydroxide ion concentration, its Kb is going to be higher because they are directly related. But pKb is going to be smaller. As we know that when you put a larger, when you have a Kb, okay, larger value of Kb, the pKb is going to be smaller. Got it? Because that is minus log of Kb. So whenever you put a minus sign, the larger value become that much smaller by becomes very small, okay, and the smaller value doesn't decrease by so much extent. So I mean to say is Kb and pKb are inversely related. If the basic strength is more, Kb is more, and if Kb is more, pKb is less. Okay, so sometime, because why am I telling this, because sometimes they ask you to compare the basic strength. So that's a direct question. Sometimes what they do, they ask you to compare the Kb order. So Kb order and basic strength order are going to be same. More basic, more Kb. Got it? Clear? And but if they ask you to compare the pKb order, pKb and basic strength are inversely related. Stronger base will have lower pKb value. Okay, so this is you need to keep in mind while solving the question, because sometimes in spite of knowing everything, just we give the wrong answer because um, in examination, due to examination pressure, you are not able to recognize that they have asked pKb value, which is just the reverse of basic strength. Okay, so this is basic strength for amines. Again the same thing, you can write this expression. And but there is a important point. What all factors are going to affect the basic strength? So for that, I'm going to tell you one thing. And that is, suppose if you have NH3, okay, and suppose you have CH3 NH2 methylamine, then you have dimethylamine. Got it? And then you have trimethylamine. So you can have these amines, and you can compare the basic strengths. So primary, secondary, tertiary amine. Got it? So basic strength increases with the electron donating power of the group. Why? Suppose if you have an alkyl group, that alkyl group is electron donating. Electron pushing group. So it is going to make the nitrogen more negative because it is pushing the electron towards the nitrogen more. If and how it is pushing, it could be pushing by its plus I effect or resonance effect. So basic strength is going to increase. Basic strength will increase with the increase in electron donating power of the alkyl. Got it? This should be clear. And if you have electron withdrawal, so Kb increases, and if Kb increases, pKb decreases. Got it? So electron donating groups increase the basic strength. Electron withdrawing groups, like you have NO2, Cl, they are going to decrease the basic strength. So I'm writing this group as electron withdrawing group, EWG. Example, you can have NO2. There are many such groups, okay? CF3, they are highly electronegative, okay? They could be exerting minus R effect or minus I effect. So these are electron withdrawing group. And if you have nitrogen, because they are pulling the group bonded electron pair, and they may also pull the lone pair. So lone pair is not available now. If the lone pair is not available, means it is less basic. Now it has not remained basic. Got it? So its Kb is going to be less. Its pKb is going to be more. This is one thing you need to keep in mind. Clear? And if I compare the basic strength of methylamines, so what should be the basic order of their basic strength? So there are two answers to it. So be careful what has been asked, and accordingly you should give your answer. There are two answers. So first one is the suppose if you have in gas phase, NH3, in gas phase the answer is very simple. Why it is very simple? What could be the reason? Meera and Upasna, why the primary amine is more basic than the rest? Ammonia, and ammonia is more basic than, or dimethylamine is more basic than methylamine, or trimethylamine is more basic in gas phase. Okay, because you have electron donating groups. Methyl will exhibit plus I effect. Okay, the more number of groups you are having, the more basic it will be. Got it? So I hope that is clear.
Yes, sir.
Okay, in gas phase. So this is not a problem. More alkyl groups, more basic, more Kb and less pKb. But the problem comes when the question asks about the basic strength in aqueous medium. So can you tell me what is the basic strength of these amines in water? In aqueous medium means when you put these amines in water, what is the basic strength, order of basic strength? So now there is a problem little bit. The order is not uniform. It is like this. So secondary amines are most basic in water. So what's the reason? Can you tell me? Normally the tertiary amines should come first because you have more number of alkyl groups. Got it? So that should come first. But something else is maybe happening and which is causing the secondary amine to be most basic and the tertiary amines to be not as basic as what you expected from their trend. So I hope this is clear. So first you need to remember the order. So in water, secondary amines are most basic. Got it? So keep this in mind. But why it is happening in this way? What is the reason? What is the reason? The reason is in water, there is a hydrogen bonding which is happening. Okay, look. This was in the gas phase. Okay, the more branched it is, more basic it will be. But in water, in aqueous phase, the order actually got disturbed. And in water, the secondary amine with two groups is the most basic one. Followed for ethylamine, it is the tertiary, and then ethylamine, and then ammonia. For methylamine, secondary, primary, and tertiary. For ethylamine, this is from your NCRT only, okay? Ethylamine, it is going to be secondary, tertiary, primary, and ammonia. So one thing is common, that the secondary amines are actually more basic in water, but in gas phase the tertiary amines are most basic as per the inductive effect, plus I effect. But why it is happening in this way? It is happening because of there are two factors which are playing the role in water. There are two factors in water. There is a factor which is hydrogen bonding. Got it? That cannot happen in gas phase. So no hydrogen bonding was there. So if no hydrogen bonding was there, it meant that more the plus I, more electron rich the nitrogen will be, and more basic it will be. So I hope this is clear. Got it?
Yes, sir.
But in water there are two opposing factors. If I talk about hydrogen bonding, this should form. So once it accepts the H plus, it forms ammonium ion. So as per the hydrogen bonding, the ammonium should be maximum stable because it has 4 hydrogens and it can make more number of hydrogen bonds. So as per the hydrogen bonding, the basic strength should increase towards the NH3. But as per the inductive effect, the basic strength should increase towards the more number of alkyl group. More and more alkyl group, more basic. So that is why this order got disturbed. Okay. So you need to remember, in water, secondary amines are most basic. For methylamines, the order is in water. The order is dimethylamine, methylamine, trimethylamine, and NH3. For ethylamines, okay, the order is diethylamine, triethylamine, ethylamine, and ammonia. So I hope this is clear to you. Got it? But you need to remember, because you can't predict on your own. You need to have this in your mind. What is the reason which is happening? And a lot of questions are borrowed from the AIMS pattern in NEET, where they actually emphasize on the explanation part, and they become more tricky question. Though there is no in reason assessment question, a statement based question, one thing is easy. It appears easy that there is no calculation involved, but actually uh, they can, but there is another risk. There is no calculation, but actually these type of questions which are actually based on explanation, and they test your understanding, in-depth understanding. Okay, so you should be quite confident that why it is happening in water, why the basic strength order is disturbed in water. It is because of the hydrogen bonding, which whose order is different from the order of the inductive effect. Got it? So this you should remember, very important. So this I hope is clear to you. Do remember it. You need to remember this thing in water. But if somebody asks you in the gas phase, no need to worry. More alkyl groups, more basic. There it is simple because there is no hydrogen bond. So what about the basic nature of aliphatic amine and aromatic amine? This is aliphatic amine, and this one is aromatic amine. Aniline. Which one do we expect to be more basic? It is the aliphatic amine which is more basic. So what's the reason? Reason is quite simple. This aliphatic group will show plus I effect because nitrogen is more electronegative than the carbon, and the electrons are the sigma bonded electrons are going to get pushed towards the nitrogen, making it more electron rich, and it will attract the H plus more strongly. It is more basic. That's it. Got it? But aniline is less basic, and phenylalanine is further less basic. What's the reason? Reason is quite simple, that the lone pair of NH2 is not fixed. It is actually delocalized. It has moved into the ring by resonance. And if it has moved into the ring, look, these are the resonance structures of aniline. So the lone pair which was there on the nitrogen is not on nitrogen. It has moved to the ortho position. It has moved to the para position. You can see the resonance structure again to the ortho position. So basically it is now dispersed, and then if you try to take the average charges, you have delta positive charge on NH2. You can see from the individual resonance structure. And if you have a delta positive charge, such kind of nitrogen, is it going to come and get attached to the H plus? H plus is also positive, and the nitrogen is also gaining some positive charge due to resonance. So what is happening? So basically now we know that it is not basic, very less basic. Okay, because of the resonance, the lone pair got delocalized to different places. The basic strength will decrease, and this is going to be further very less basic. Why? Because the delocalization is even more than aniline. In aniline, which I have written below, the lone pair of nitrogen got dispersed at 4 places: nitrogen and 3 on carbon, orthopara positions. So it got distributed at 4 places. And in diphenyl amine, it is dispersed at 7 places. Okay, there are ortho positions and para position, 3 ortho para position in one ring, 3 ortho para positions in another ring. And there is nitrogen also in addition to the ortho para position, the original position where the lone pair was originally from, where it started. For total 7 places it got distributed. So such electron density will be very less available for the incoming H plus. So it is going to be least basic. So if you disperse the lone pair by resonance, the basic strength will come down, Kb will be come down, and Pkb will be more. That is going to increase. I hope this is clear to everyone. Got it? Further, suppose if you have a group like OCH3, CH3, they will increase the basic strength because they are electron donating groups. But if you have electron withdrawing groups on the benzene ring, they are going to decrease the basic strength. Okay, clear? So let's do one question about the basic strength of anilines. So what will be the basic strength of these four amines, anilines? These are substituted anilines. What will be the basic strength? You can easily compare by trying to focus on the difference. Look, this part which is above this line is same for all the amines, right? It is same. So we should not compare this. Okay, we should talk about the group which is placed at the para position. That is different. This is the difference. And now we need to check this group is actually, is it increasing the electron density or is it decreasing the electron density? Out of all the four groups, you have D. In D, you have hydrogen, just hydrogen, no other group. Means the electron density is neither being increased nor being decreased. Got it? It is just at the neutral level, the reference. But if you compare OCS3, OCS3 will give the electron pair plus R effect or plus M effect, I can call. It is going to increase the electron density to negative charge. It can increase the negative charge. And you can observe that the negative charge is increased and ultimately it is going to increase the negative charge on the nitrogen. And it is going to be more basic. Got it? So electron donating group will increase the basic strength. So electron donating groups are C and A. But C is causing the increase in electron density. C is causing the increase in electron density by resonance. So that is plus R or plus M effect. And A is causing the increase in electron density by plus hyperconjugation effect. Okay, hyperconjugation effect of methyl. And resonance effect is more strong. Okay, so if the resonance effect is more stronger, so you have most C to be most basic, followed by A, then D, and but B is least basic because NO2 is going to, NO2 is having a positive charge on nitrogen. Got the point? So it is actually withdrawing the electron density from the aniline. So now aniline is less basic because its electron density has been removed by NO2 group. It is NO2 is the group which will pull the electron towards itself by resonance. Okay, it will withdraw electron, and if the electrons are withdrawn, how can it be basic? Okay, so C, D, and you have B. Okay, so I hope B is a you understood this. Meera and Upasna, is it clear?
Yes, sir.
Yes.
Okay. Now you have some other groups which are placed at ortho and para position. Suppose if I ask you to compare the basic strength of aniline, if I ask you to compare its basic strength with para nitroaniline, beta nitroaniline, and ortho nitroaniline. So what is going to be the correct order of basic strength? Decreasing basic strength. Got it? Decreasing basic strength. So first of all, one thing is clear that all these three, rest of the three benzene rings have electron withdrawing group, which is the nitro group. Wherever it is placed, either at ortho position, meta position, or para position, one thing is sure that it is going to remove or suck out the electron density, and it is going to make the aniline less basic. So one thing is sure that B, C, and D are less basic than A. But within BCD, what's the order? Okay. So now we know that this lone pair will get into the ring. It will come at the ortho position and para position. It will come at the ortho position and the para position. Just now we have seen the resonance structure. If you can recall this one, you can see the minus charge is coming at the ortho and para positions. Got it? So here also it is going to come the lone pair. When it will undergo resonance, it will come at the ortho and para. So that is same because you have a benzene ring. But now what is the effect of NO2? NO2 will further take away this negative charge. So I should say the NO2 at ortho and para position can participate further in taking the electron pair or the lone pair. It will exert minus R or minus M, if you can say, both are same, and minus I effect also. But the NO2 group which is placed at the meta position will not be able to accept the lone pair of NH2 because that minus charge is not passing from the carbon bearing the NO2 group. So NO2 is exerting only minus I effect, no resonance effect is being observed as far as the negative charge is concerned. Okay. In case of D, the NO2 will exert minus R effect, that is true. It is also going to show very strong minus I effect because it is very close to the NH2. So that NO2 has positive charge on nitrogen. It is going to withdraw the sigma bonded electron pair. So it is going to pull the electron density of NH2 very strongly. Got it? Okay. So D is going to be least basic. Okay, D. Followed by B, where the NO2 is participating in resonance, and C. C is less basic than A, but not the least basic, because the negative charge is not getting on to the nitrogen. It is passing from the position which is just adjacent to the NO2, not directly on the position where the NO2 is attached. So there is no resonance effect, no electron withdrawing group other than the benzene. Here in the case of C, you are having the NO2 group, which is exerting only minus I effect. In B, you are having minus R effect and minus I effect. In D, you are having minus R and strong minus I effect because it is closer to the NH2 group. So this is the order. Got it? So I hope this is clear to you. Very, very
Yes, sir.
important. Okay. So this is the order of basic strength. Now next reaction is acylation and benzoylation of amines. This also plays a very important role. And I told you there are two functional groups which can undergo acylation or benzoylation, and they are alcohol and amine. Okay. Alcohol and amine can undergo acylation or benzoylation. Acylation means putting acyl group. Acyl is COCH3. Okay, COCH3 group. And benzoylation is COPH, benzoyl group, attaching benzoyl group in place of hydrogen. Okay, this is acylation. So primary amine can undergo acylation. Secondary amine can also participate in acylation. HCl can be removed by base, and you, in place of hydrogen, you have this COCH3. Acylating agents are CH3, COCl, or acetic anhydride. Acetyl chloride, this can also be called by the name of acetylation, or acetic anhydride, which is the common name. You can, the IUPAC name is ethanoic anhydride, can be used for carrying out the acetylation of NH2. Means you are putting acetyl group or benzoyl group, benzoylation, in place of H. Got it? So this is, you end up with an amide. This is also an amide. Got it? If you carry out the acetylation of aniline or benzenamine, the product is known as acetylated aniline, which is a very common reaction. This is methylation. This is methyl benzene, methylamine, and you are carrying out benzoylation. You are attaching this benzoyl group by removing HCl. So you have this benzoyl group connected in place of H. You can see the HCl is removed, COPH is going to come and attach. And this is known as N-methyl benzenamide. Clear? So this benzoylation has a name. Can you tell me what's the name is if you remember from NCERT? Benzoylation reaction. Schotten-Baumann reaction. Understood? Any doubts in this? Clear?
Yes, sir.
Okay, great. So acetylation or benzoylation. Okay. But tertiary amines cannot undergo acetylation reaction. Why? What could be the reason? Tertiary amines. The answer is simply no reaction. So what is one basic thing which is missing here, and that has not let the tertiary amine to participate in acetylation or benzoylation? What is missing?
Hydrogen
The
atom.
hydrogen atom is missing. Exactly. So tertiary amine cannot undergo acetylation or benzoylation reaction. Primary and secondary amines can. Okay. So this is one of the reaction. The other reaction is actually the test for amines, and this is isocyanate test or Hoffman carbylamine test. This is for primary amines or 1 degree amines. So what are the reagents and what is the outcome? Only primary amines give this test. First of all, the outcome is, the reagents are, you treat the primary amine, you treat them with chloroform and base. In the present, you heat them, and this chloroform and base, there are HCl, you can see 3 HCl, they get removed, and this nitrogen and carbon get clubbed together to form NC, isocyanide. This isocyanide has a foul fishy odor. And if you observe this kind of odor, means the amine which you have taken is primary amine. Got it? Clear? Both aliphatic and aromatic amines can give this reaction. Aniline also can, because it is a primary amine. You need to have NH2 group. If you have NH2 group, a reaction can happen. Got it? So aniline also can give this reaction. As you can see, the aniline has NH2 group. And what happens with this, when you take CHCl3 and KOH, the CHCl3 and KOH, actually HCl is removed in the presence of base. You can see this is chloroform. You have taken base, base will remove the H plus. You are going to get CCl3 minus, the Cl minus will be removed. You are going to get a carbene. Okay. This carbene, though it is neutral, but it has incomplete octet. It has only 6 electrons. So it get combined with the lone pair of aniline because it want to accept electron, and lone pair is freely available. So you have this kind of intermediate which is being formed, and because you have taken an acidic base KOH, so HCl will be removed. HCl will be removed one by one. Okay. So you will end up with a triple bond NC isocyanate. That's how the reaction happened, and this is the mechanism. I have removed HCl together, or this is the actual step. The first Cl comes out, then the next chlorine comes out. Got it? And that's how you get the final product isocyanate. So I hope this is clear to you. The mechanism is clear, the reagent is clear. Any doubts in this?
No, sir.
Okay. So only primary amines will get this test. Secondary and tertiary amine, they will not give this test. Okay, secondary, tertiary amine cannot give this test, only primary, because they have that NH2. There are 2 hydrogens, so they can remove and form a triple bond. Secondary and tertiary amine, secondary amine is having just 1 hydrogen, tertiary amine do not have any hydrogen. So they will not give isocyanate which contain N triple bond C. Got it? So this is very, very important. So just we will do some question. Normally, to complicate the situation, they give IUPAC names. So, which of the following compound can give isocyanate test? The question is very simple. If I would have given you the structures, this is a direct question. But in order to increase just some, add to some complications, I have given you the IUPAC names. And why I have given? Because I need to communicate one point that you should be quite familiar with the IUPAC names also. Okay. Because in a lot of questions you expect them. Sometimes you know the question, but you make a mistake, silly mistake, just because of the name. You made some mistake in deciphering the name correctly. So N-ethyl propanamine. N-ethyl propanamine is, you have propane and you have amine, and on N you have ethyl. Okay, this is the structure. Next is 2-methyl propan 2-amine. Prop has 3 carbon atom. 1, 2, 3. You have amine on the second carbon atom, NH2, and on the second carbon you have methyl also. N-dimethyl methanamide. Methanamide is N-dimethyl, and this is the methanamide. Benzenamide is PHCONH2. So definitely this is a secondary amine. This is not going to give this test. Got it? Clear?
Yes, sir.
This is primary amine. This can give this test. This cannot give the test. And what about this one? Though there is NH2, but this is not an amine. This is amine. So amine cannot give this test. Means amide cannot give this test. Okay. This test is only for primary amine, not for amide, because this in basic medium it will get hydrolyzed to carboxylic acid. You need to have this kind of, you need to have RNH2, not this kind of amide. This is not an amide. Amides do not give this test. So I hope this is clear to you. Got it?
Yes.
So need to be comfortable with the IUPAC names. Okay, suppose if N is written, so the trick is NN is written means you have 2 alkyl groups, or if the N is written means you have 1 alkyl group more. So that is going to be secondary. Got it? Clear? Okay. So this is very, very important. I hope you understood. Okay. Next reaction is NaO2 plus HCl. This also is a very important reaction, NaO2 plus HCl or HNO2. Because NaO2 plus HCl react and give you HNO2. So nitrous acid, reaction with nitrous acid, reaction with NaO2 plus HCl. So the reaction can be used to detect the amines. How it can be used, and it can also be used to convert amines to alcohol, primary amines to alcohol. So we have two purposes here being solved. The first is detection of amines, the type of amine, whether it is primary, secondary, or tertiary. Next is it can be converted to an alcohol. Got it? Is it clear or not?
Yes, sir.
So when you react with NaO2 plus HCl, you get diazonium salt, N2 plus and Cl minus. And this N2 plus and Cl minus, upon heating, it breaks, giving us N2 gas, and the water get attached to the carbocation, and you have an alcohol. Okay. So this is the conversion of amines to alcohols, right? Amines are being converted to alcohol by using NaO2 and HCl. This is one thing. And this reaction is also holds a very important place in aromatic amines or in aniline. In aniline, when you treat them with NaO2 plus HCl, and you deliberately keep the temperature low between 0 to 5 degrees to hold the reaction. Okay. There was a question in NEET where they gave that the primary amine react with NaO2 plus HCl at 373 Kelvin. Everything was correct except one thing. 373 Kelvin, that is 100 degrees. That was wrong. 100 degrees, it will break actually. Okay, you need to hold on to this. So for that, you need to keep the temperature 0 to 5. So I mean to say here is, in your statement based question, read each and every word, each and every data clear, very carefully you have to read, because suppose by chance if you miss to read the data, okay, suppose the initial part of the statement may appear correct, and based on that I tick mark that whole statement to be correct, that it may go wrong actually. You need to look at the temperature also. You need to read each and every data in the sentence completely till the end. Okay, and then only you should come to the conclusion whether the statement was right or wrong. So this is clear. So with aniline, this holds a very important significance. You hold the reaction and you stop the reaction temporarily, not permanently, at diazonium. Okay, this is the diazonium, preparation of aryl diazonium salt, but it is going to stay if you keep the temperature low, 0 degree or 0 to 5 degrees. Now what's the significance? Why we want to hold the reaction to diazonium? The reason is we can stop the reaction, and we can put the group of our need or for our desire in place of N2 upon heating. Okay, clear? So this is basically the conversion of the diazonium. We have seen this reaction. Where we have seen this reaction earlier? Any idea? Where we have seen this reaction in aroma, in aryl halides also we have seen this reaction where we were converting the aromatic diazonium salt into chlorobenzene. Suppose if you want to get the chlorobenzene, what you need to do? You need to heat it with CuCl and HCl. You will end up with a chlorobenzene. If you want to prepare bromobenzene, look here. You need to heat it with CuBr and HBr. If that is Sandmeyer reaction, if you heat it with copper powder, that is Getterman. The name changes, but the product will remain same. If you heat with CuCN and HCN, you are going to get benzonitride. If you heat it with Ki, you are going to get iodobenzene. If you heat the diazonium salt, so that's why I told you to take the initial temperature while you are preparing diazonium to 5 degrees. Keep the temperature low, so that the diazonium can stop, the reaction can stop at diazonium. In the next stage, we actually put the group that we want to connect, either Br, Cl, Cn, and then we can heat it. Okay, but during the preparation you should keep in mind that you should not take high temperature. You should keep the temperature low. I hope this is clear to you. Okay, if you want to get a phenol, this we have seen in preparation of phenol. Okay, you can heat the diazonium salt with H2SO4 and dilute it. The H2S dilute H2SO4 aqueous in aqueous medium, or H2O heat also is sometimes written H2OH plus heat. The water is going to come and attack, and you are going to end up with phenol. This is Shishman reaction, where you are heating the diazonium with HbF4. HbF4 can be written as HF and BF3. Okay, HF and BF3 can be written. So there you can get the fluorobenzene. Okay, fluorobenzene directly it is very difficult to synthesize, because we know that fluorobenzene is basically fluorine is highly reactive, so you can't prepare it directly. So you need to prepare by this method, and this method is known as Shishman reaction. Sometimes you need to convert the diazonium back to H3PO to benzene by heating with H3PO2, or you can use ethanol and copper. If you treat this diazonium salt, so this set of reaction is different. What these reactions are known as? These three reactions. Can you tell me? If you remember, Miranopasna. These are known as diazo coupling reaction, because your coupling is being taking place. So in this, you don't remove the N2. This molecule as such will go and get attached to the phenol or aniline at the para position. So this this diazonium will get attached to the para position. You can see para position with respect to phenol, para position with respect to aniline. The only difference is in phenol you take slightly basic medium. Why you take basic medium in phenol? Any idea? Meera and Upasna, any idea about it? Why you take basic medium? Because phenol become more reactive in basic medium. Got it? What you get from phenol? You get phenoxide ion O minus, which becomes basic. Okay, and it become more reactive, so this diazonium cation get joined on the para position of the phenol. On the other hand, in aniline you require slightly acidic medium. Okay, slightly acidic medium you require for the aniline. These are diisocoupling reactions and they are colored. This is orange colored compound. These are dyes basically. And this is yellow. So I hope this is clear to all of you. Any doubts in this? Okay.
No.
So, but do keep this in mind. It is very important reaction. Okay, there are two sets. In this also we have classified two reactions where you are breaking the N2 and putting some group, and that group cannot be put directly. So you are using it. You are putting it by the means of diazonium. And in the other case, you are joining this diazonium cation at the para position of phenol or aniline. As a diisocoupling reaction that lead to the formation of colored compound known as azo dyes. Okay, azo compounds or azo dyes. They are colored. Got it?
Yes, sir.
So next is, so this is very important reaction. And next is Hinsberg test or Hinsberg reagent. Got it? Hinsberg test and Hinsberg reagents. First of all, what is Hinsberg reagent? That you should know. That is very simple. Hinsberg reagent is benzene sulfonyl chloride. Okay. And it can react with primary and secondary amines, but not with tertiary amines. What's the reason? The reason already we discussed. What's the reason why tertiary amines will not react with the Hinsberg reagent? The reason is same.
There is no hydrogen.
No hydrogen available. Okay. So as far as test is concerned, somebody may give you some formula. For example, C3H9 and somebody may give it in the form of question and tell that it do not react with benzene sulfonyl chloride or Hinsberg reagent, means that is confirmed that it is tertiary amine because it doesn't have H. Primary and secondary amines can react because they have primary is having 2 hydrogens, secondary is having just 1 hydrogen, so they can react. So you can see here the primary amine, this is primary amine, and it can react with the Hinsberg reagent. HCl will be removed by base. Okay. And secondary amine, diethylamine, that also can react, okay, by the base. In the presence, base you need because you need to remove HCl. Got it? Minus HCl. Right? And whatever you get is known as, that is known as sulfonamides. So for primary amine, you will get N-alkyl sulfonamide because there is only one alkyl group in the primary amines. So N-alkyl, whatever the alkyl group, N-ethyl, N-butyl. In second, and this you are going to give N-diethyl sulfonamide, benzene sulfonamide. Okay, clear? So accordingly you can take. But how you are going to distinguish? There is one H still, one more H still left on the sulfonamide in case of primary amine. One H is left, and because one H is left, it can react further with base. This H can be removed by base. So sulfonamides of primary amine are base soluble. Sulfonamides of secondary amines will not react further with base. Why? What could be the reason? What could be the reason? They do not react with NaOH or KOH. Because they do not have any hydrogen. Okay, so it will not react. So sulfonamides of primary amine are base soluble. Sulfonamides of secondary amine do not react with base. They are insoluble in bases. So this is the statement which you need to check for in the question, and with that you can make out whether the amine which is given to you is primary, secondary or tertiary. Got it? Is that clear? And tertiary amine do not react, they do not form sulfonamide. I hope this is clear to everyone.
Yes.
Okay, so do keep this in mind, very important. Tertiary amine do not react, do not form sulfonamide. Primary amine can react with Hinsberg reagent to give you sulfonamide, and though their sulfonamides are base soluble, and secondary amines can react with Hinsberg reagent, and but they will not react with bases further. Okay. Next, move on to the reactions of aniline. The basis for the reaction of aniline is its resonance structure. Got it? The resonance structure. Aniline, you know, just now we previously also while discussing the acid base strength, I told aniline. Okay. It undergoes resonance and the lone pair of N moves at the ortho and para position. And this makes ortho para position rich in electrons. So what are the centers of reactivity where reaction, electrophilic reaction is going to take place in aniline, that is at ortho and para position. I hope this is clear. And why ortho positions and para positions of aniline are highly reactive? Because the electron density is increased by the resonance caused by the lone pair of NH2. Are you getting my point?
Yes, sir.
Okay, great. Now the ring becomes so rich in electron density that if you react it with bromine water, automatically the bromine is going to come at the three positions, ortho and para positions, and you are going to end up with tribromo. Same is with the phenol also. Phenol, if you react with bromine water, you are going to get tribromophenol, which is the white PPT, and where the three bromine are going to come and join. They are going to come and attach themselves to the ortho and para positions. Is it clear?
Yes, sir.
Got it? Okay, great. Now, suppose in a conversion, if someone asks me to put only one bromine, just one, then it is a problem for me. Because if I react it with bromine, the reaction is taking place very in excess amount, okay, and because it is highly reactive, so all the three position, ortho and para position, are being taken away by the bromine. So you get bromine attached at all the three positions. But suppose if a reaction demands, in the question it is asked to put just one bromine, then how we are going to do that? How we are going to do that? So then we need to reduce, we need to put a brake on the electron density on the benzene. When you had aniline, it was highly electron rich ring. Got it? The electron density was coming on ortho and para positions. So all the ortho para positions were very highly electron rich. And that's why the reaction was taking place at all the three positions. Okay. Now, but if you want a limited reaction to happen, you need to put a brake on the electron density. You need to put a brake on the lone pair which was getting into the ring. So how to put a brake? How to stop that lone pair getting into the benzene ring? The answer is very simple. By carrying out its acetylation. Acetylation can be, just now we have seen in today's class only, acetylation can be carried out with the help of CH3 COCl, either acetyl chloride, or you can use acetic anhydride. These are the acetylating agents, and it can bring in the acetyl group on the nitrogen. What happens if the acetyl group come on nitrogen? This acetyl group stops the lone pair completely getting into the benzene, because now, as you can see here, the lone pair can now undergo resonance with the CO also, and it can undergo resonance with the benzene also. So now the lone pair is distributed on the two sides. So the benzene electron density is not very much. Okay. Now it has stopped increasing by large extent. Earlier it was very largely increased. Now also it is increased, but by lesser extent. And this acetylated aniline is known as acetanilide, that is a short form, or N-phenylethanamide. Because the electron density is less, because it is being distributed on the either side of the nitrogen. Now if you react with bromine, you will have just one bromine attached, not the three bromines which were actually which you were seeing earlier. The bromine were being attached at all the three positions. Now you will not see that. Got the point? Now just one bromine, because the electron density has decreased and the ring is not that much reactive now to undergo bromination three times, just one time bromination. And para position is much preferred. Para product is a major product. Can you tell me why ortho is not formed? Ortho also carries a negative charge. What could be the reason? Meera and Upasna. Why ortho is not formed? Because this group, you can look at the size. It's very huge. Okay. And ortho positions are actually historically hindered. The attack on the ortho position is prevented. Got it? It's difficult to come closer to the ortho position because of this large size group, which is stopping the attack at the ortho position. Okay, once the reaction is completed, you can break this amide by taking water H plus H2O, H minus H2O. You can hydrolyze it. Okay, and you are going to get 4-bromoaniline. This is how, this is also known as protection of aniline by acetylation. Okay, and this is the next reaction which is being asked many times in JEE advanced also. Okay, everywhere, lot of examinations, JEE advanced, JEE main, so it has been asked in many examinations. Got it? Very common reaction. And the reaction is nitration of aniline. Okay. So first of all, what happens upon nitration? If we carry out the nitration of aniline, what happens? NO2 group get attached. Nitrating mixture you take, HNO3 and H2SO4, you heat it. And one thing is, because the aniline is highly electron rich, you expected the NO2 group to get attached to the ortho and para positions. So you get para position because NO2 is a larger group, so it will prefer to join itself to the para position, 51% para. Ortho, but ortho is very less, very less. So this is surprising. And there is one more surprise. The meta product is too high. It is 47%. We have not expected the meta to form because there was no negative charge. Meta position, no delta negative charge was there. So how come this NO2 group managed to attack on the meta position in spite of with no charge? Okay, why ortho has not formed in large amount, though the ortho positions were there, they were having high electron density. So these are certain questions which are which come to our mind, and they are also the favorite questions for your competitive examination. In reason and assertion based question, they can be asked. And overall the yield will be very low. There will be lot of, so among the whatever you get, first of all, whatever you get, that is going to be very less. And whatever you get out of that, 51% is para-nitroaniline, 47% is meta-nitroaniline, and 2% is ortho-nitroaniline, which is again surprising. Okay, and this is very less part. Actually, lot of tarry products, they also form. Okay, lot of oxidized products get formed because HNO3 is an oxidizing agent. It oxidizes the aniline. So overall yield is very low because of the high electron density of aniline. Okay, the aniline actually forms, and this is a strong acid, so it forms an aniline ion, NH2 plus, NH3 plus, so which due to which you get a meta product. Aniline also get oxidized by nitric acid, due to which you get a lot of tarry products, mixture of products which contain oxygen. So this reaction is of no use because you are getting so many products and not sure about the major product. So how to carry out the nitration? The answer is again the same. Don't carry out the direct nitration. Got it? Clear? Because direct nitration is causing lot of problems like oxidation, loss of yield, multiple products being formed, unexpected meta product being formed in a large amount. So don't do the nitration, direct nitration of aniline. First, go for the acetylation of aniline, which will put a brake on its electron density. Are you getting my point? So first of all, I carried out the acetylation, which is very simple. You already know it by taking CH3COCl or acetyl chloride. You get acetanilide, and then you carried out the nitration. Now the electron density is not that high. Meera and Upasna, is it clear or not? Tell me quickly.
Yes, sir.
Okay, now you can. Okay, good. Now you can, once you have a protected aniline, this is known as protection of aniline because you are putting a brake on the electron density. Okay, and now you can carry out the nitration. Okay, and you will see that the nitro group get attached to the para position. Once the reaction is complete, you can break this protection by heating with H plus H2 or OH minus H2. You will get this. Okay, so this forms a very important part. You can see a lot of questions are there being asked on this. Okay, next is sulfonation and diazocoupling reaction. You can do the sulfonation of aniline by heating with concentrated H2SO4. If you don't heat, first of all, if you just mix H2SO4 and aniline, you will observe that there is a salt formation, NH3 plus and HSO4 minus. When you heat it up to 200 degree, then the sulfonation takes place at the para position, and you get a sulfanilic acid. There is a famous question that sulfanilic acid exists as a zwitterion. Got it? Why it exists as a zwitterion? What could be the reason? Why sulfanilic acid can exist as a zwitterion? What is zwitterion? Zwitterion is a dipolar ion. Okay, where you get a positive charge and negative charge. Okay, you get a positive, and why the positive and negative charge come up? Because This is a base and this is acid. So acid donates is H plus and base accept H plus. So you have this kind of dipolar ion with opposite charges, and this is known as deuterion. So this is a very famous question, that why deuterion is formed. So I hope this is clear to you. Got it? Clear?
Yes, sir.
Okay. Now aniline uh, can be combined with the diazonium. That is known as what kind of reaction? Diazocoupling reaction. Okay, diazocoupling reaction of aniline. So this diazonium you already prepared, that also is prepared from aniline only, but if you react it back with aniline, this diazonium will get attached to the para position of the aniline. Okay, just now we discussed, and you are going to get a yellow colored compound, which is a dye, azo dye. And I told you this azo dye can be used to test the aniline or phenol also, and this reaction come under diazocoupling reaction. Got it?
Yes,
So now
sir.
let's move on to the next chapter, and that is coordination compounds. Let me go through quickly through the basic definition. There are double salts and there are coordinate complexes. What is the difference? What's the difference between the double salt and complexes? Any idea? Double salts like potash alum. Got it? Potash alum, if you put it in water, what happens? It splits completely into its ions. Potassium, aluminium, sulfate. It's completely split because they were having ionic interaction. More salt. What is more salt? Ferrous ammonium sulfate. More salt. That also is a double salt. And complexes do not split completely because complexes have their components are held by coordinate covalent bond. Okay, their their components are held together by coordinate covalent bond. Okay, for example, if you have AgNH3 whole twice plus, or if I write it like this, AgCl dot 2 NH3, it will be like this. So these NH3 molecules are bonded to a silver by coordinate covalent bonds. Got it? And because they are bonded by coordinate covalent bond, they are not going to split. Covalent bond do not split. Ionic bond get dissolved. Ions get dissolved in water. Got it? So this is, so it do not lose its identity, and it is going to remain as AgNH3 whole twice plus and Cl minus. Got it? So now the original ions are now changed to new ions, and the new ion do not split completely. Okay. For example, so now Ag plus is not there. Okay. For example, if you take FeCl3, FeCl3 is basically Fe3 plus. And if you take this is potassium ferricyanide. So this also has Fe3 plus, but that Fe3 plus is not actually dissociated completely. It is going to the Fe3 plus is not alone now. Now it is being surrounded by cyanide ions. Got the point? So Fe3 plus, it will not give the test of Fe3 plus. Got it? I hope this is clear to you. Okay. So then you have the nomenclature. In nomenclature, the type of, then you have types of ligand, types of complexes, nomenclature. Okay, the basic introductory part of the coordination compounds. Okay. And in this, first of all, types of complexes, you have homoleptic and heteroleptic. What do you mean by homoleptic and heteroleptic complex? Homoleptic means they consist of just one type of ligands. Okay, and heteroleptic consist of more than one type of ligands. Okay, for example, this is homoleptic. And this is heteroleptic. Can you name which is this reagent? Meera and Upasana, what is the name of this reagent? This is also a very famous reagent used elsewhere. This is sodium nitroprusside. Okay, there is a sodium nitroprusside test also for the detection of sulfide. Got it? So this is heteroleptic and homoleptic, that you know already. And now the type of ligand. Ligand can be classified on the basis of charge. Negatively charged ligand are the most common. Their name end with a suffix O. For example, chlorido, bromido, iodo, cyano. Got it? Or chloro, bromo, iodo. There are neutral ligands also. Negative ligands, neutral, and positive ligands. Negative ligands like chloro, bromo, iodo. Cyano. Or chlorido. Bromide. Earlier name was bromo and now it is called bromido. So both are used. There are neutral ligands also. What is the name for H2O? Tell me.
Aqua.
H aqua, and this is pyridine, right? What is the name for CO? CO is basically it is carbonyl. Got it? It is carbonyl. NO is nitrosyl. Okay. Positively charged ligands end with a suffix em in their names. For example, this is hydrazinium. Okay. Here. So ligands can be classified on the basis of charge.
Yes,
Ligand
sir.
can be classified on the basis of their denticity. What do you mean by denticity? Denticity is the number of lone pair which a ligand can donate to a single metal atom or ion. Denticity, you can classify the ligand to be monodentate. Bidentate or didentate. Tridentate. And so on. Tetradentate, pentadentate, hexadentate, like this. So these polydentate ligand must have more than one lone pair. There are also monodentate ligand which can be considered to be ambidentate. Got it? So monodentate, these were all monodentate ligand. Cl minus, Br minus, I minus. Okay, they were all monodentate ligand. Bidentate ligand, can you give me the example of bidentate? Any bidentate ligand? Meera and Upasna, can you give me the example of bidentate ligands which carry two lone pair? Any idea?
Oxalate.
Oxalato. Yeah, it is negatively charged, so I'm going to write it as oxalato. Correct. Very good. And then negatively charged bidentate ligand, you have NH2, NH2. So what this will be known as NH2, NH2. What you will call this?
Ethylene diamine.
ethylene diamine, and the other name is actually ethane 1,2 diamine. Okay, ethane 1,2 diamine. Got it? Ethylene diamine or ethane 1,2 diamine, right? Uh, as per the latest convention, it is called ethane 1,2 diamine, and there is also one very common unsymmetrical bidentate ligand, which is negatively charged. What's the name of this ligand? This is also there in the chapter of amino acid, the smallest amino acid. Yeah, it is glycinato. Got it? Negatively charged, so O at the end of its name. Got the point? Glycine or glycinato. These are bidentate ligand, very famous, very common bidentate ligands. Most common bidentate ligand. And when you have these bidentate ligand attached to a metal, what happens? For example, if you take Ni, if you react it with NH3, what's the name for NH3? What's the name for NH3? Amine with 2M. Okay, for everywhere you are going to just put 1M. Okay, except for NH3 where you are going to put amine. Okay, with 2M. So what's the name of this complex? Can you tell me? Hexamine nickel 2. Got it? Clear?
Yes, sir.
And suppose if I put ethylene diamine or ethane 1,2 diamine, I need just 3 of them because each one is fulfilling the purpose of 2 NH3, so I need just 3 of them. Okay, so in short form I can write it like this. If somebody asks me to draw the structure, complete structure, I can draw it, okay, like this. And this En is actually giving the lone pair, 2 lone pair. Got it? Clear? So you can see the rings being formed because, so what these complexes are known as with the rings, with the what these complexes with the rings containing bidentate ligands or tried polydentate ligands, what such complexes are known as? They are known as chelated complexes. Got it? Chelated complexes are more stable than non-chelated ones. Got the point?
Yes, sir.
So chelated complexes because they can form more easily. Okay, chelated complexes. Next is they have a high equilibrium constant for the formation. They are more stable because of the rings. The rings must be 6-membered or 5-membered, then they are more stable. Ring must not be 3-membered ring because they are more strained. Chelated complexes are more stable than non-chelated one. Okay. Suppose if you have a tetradentate ligand or tridentate ligand, then you have one ligand is capable of forming more number of rings. Okay. For example, if I give you Ni di-En whole twice. So what is this di-En? Di-En is diethylene triamide. So it is a tridentate ligand. There are diethylene and the amine will be 3. Look, this is the ethylene part. And you have 2 such portions. So this is, look, 2 ethylene part, CH2 part, and they are connected by NH2s. And on the starting and at the end you have NH2. So diethylene triamide. Got it? So this is a tridentate ligand. So I will need just 2 of such ligand because each one is giving 3 lone pair. So in order to make 6 bonds, the coordination number of nickel 2 plus is 6. The number of coordinate covalent bonds which a nickel can form are 6, but the 6 bond can be formed by just 2 di-En ligands because each one is making 3 bonds. And this is going to be more stable than this one. Okay, and this is going to be more stable than this one. Clear? I hope this is clear to you. Okay, so and there are ambidentate ligands also, right? Ambidentate, what are ambidentate ligands? Any idea? What do you mean by ambidentate? Ambidentate are monodentate only. They give one lone pair. They are not bidentate or didentate. But they can give one lone pair in more than one ways. Okay. For example, NO2. NO2 can give its lone pair from oxygen. It is known as nitrito O. And this is nitrito N. Got it? Clear?
Yes, sir.
Nitrito O, nitrito N. This is which ligand? Can you name it? The ligand is same. Actually, I am connecting it with 2 different ways. Thiocyanato S. Thiocyanato N. Got it? So nowadays, as per the convention, you write just one name and you write the name of the donor atom in capital. Okay. So these are not ambidentate ligands, are not polydentate. They are monodentate only, but they can donate the one lone pair in more than one ways. Got it? Cynato is OCN. OCN is cynato. NCO is isocyanato. Earlier name which was used was isocyanato. Earlier you used to put iso. Now you keep the name same, cyanato O and cyanato as per the latest convention. Cyanato O, cyanato N. You keep the name same and you write the capital letter. Got it? Of the donor atom, through which it will be connected to the central metal atom or ion. So I hope this is clear. Just next class we will go through some more ligands and move on to the next portion of coordination compound. By that time you can just solve your questions, okay, and let me know if